In previous, rather long lesson, we talked about how to develop an iterated integral for rectangular regions. And now we're going to look at how do we do this for areas or regions in the xy plane that are not rectangular. So our example last time revolved around the surface f of xy equals 4 with x between 0 and 4 and y between 0 and 5. So we had a nice rectangular region. If we imagine this to be inside of our xy plane, then we were focused on finding the volume of underneath this green surface along these boundaries. We found out we could do this one of two ways. We could either take the integral from x equals 0 to x equals 4, and then the integral from y equals 0 to y equals 5 of our function dy dx, which would give us the same answer as if we had integrated from y equals 0 to y equals 5, and then from x equals 0 to x equals 4 of our function dx dy. And both of those came out to be 80 cubic units. But what if that region is not rectangular? What if instead we wanted to know the volume underneath this green surface along or underneath this triangular portion? So imagine that instead what we did is we divided this region into a triangular portion, and we just wanted to know the volume inside of here underneath that. Well, one way to do it is to say we have an 80 cubic unit, 80 units cubed, and since that represents half of the entire rectangular region, if we divided that by 2, then we would get 40 cubic units. And this will only work, of course, again, if it's a triangular region or something that we can mathematically reduce to a simple formula. But if it's not the case that we can do that, then how do we do it? Well, we've already devised this double summation where we've said we could either look at, if we represent each one of these little squares as rectangular regions, and we found the volume of one of those little rectangular regions and added up all the volumes either along the rows, so I'll refer to the rows as along x, for one particular dy, or for one particular dx, we could sum up all of the volumes along these columns, that is, along the different dy's. So if we think about how this is devised, if I first of all think about summing along the columns. So what I'm referring to here is if I basically broke this up into a bunch of strips going vertically, so refer to these strips as being columns. And then what I wanted to do within each of those columns is to add up the individual volumes working my way up along each column. So let's just say that this represents a small dy by dx portion, and then I added to that the volume here, and I added to that the volume here, and all the way up until I reached, well, where do I have to stop? Well, I have to stop adding volumes once I've reached the function itself. So if I'm going to break this up into a sum along individual dx's first, individual x strips, then I want my outer integral to go from x equals 0 to x equals 4. And what that does is it basically slices this up into these individual little dx columns first, all the way up until this last one. Now remember, these are infinitesimally narrow. The integral will do that for us. We're just drawing it this way to get a conceptual sense of what's going on. Then I need to add up along each of these individual columns the individual volumes. Well, I start at y equals 0. I start down here. That's where my slices start, my strips start. But then where do I stop? Well, I stop once I hit the line. And then once I iterate to the next dx, which would be this column here, and I start slicing those guys up as well, starting at x equals 0, all the way up to, well, not until I hit y equals 4, now I'm going a little bit lower. But the thing that each of these strips has in common is that I'm always slicing until I hit the line. Until I hit the line. So what is this line? Well, this line has, I need to know its equation first. It has 2 points. It has the point 0, 4 and the point 4, 0. So I can see that that's for an increase in x of 4 units, I get a decrease in y of 4 units. So that is going to be a line with a slope of -1, so negative x, and then my y-intercept is 4, so this line can be modeled by y equals a -x plus 4. And we can just verify points. When I plug in 4 for x, -4 plus 4 is 0, and so that checks out. So that means I'm going to stop integrating when I get to the line -x plus 4. And this is going to be of the function 4, and then dy is my inner integral, and dx is my outer integral. And now I can compute this by evaluating the inner integral first. So to do that, you notice that first of all, our upper boundary involves a variable, and there's nothing wrong with that. It just means that we're going to replace y with -x plus 4 on its upper bound and y equals 0 on its lower bound. So if I focus on this inner integral first right here, which I'm going to do, then I can evaluate that. So the integral of 4 dy is 4y, and I'm going to evaluate it on the boundaries y equals 0 and y equals -x plus 4. And once I'm done with that, I'll integrate from x equals 0 to x equals 4 dx. Now, always I'm focused on what's on the inside, so now I'm going to replace y with -x plus y. So I'll have the integral from x equals 0 to x equals 4 of parenthesis 4 times y, so -x plus 4, minus 4 times my lower bound, which is 0. And once I'm done with that, I'll integrate dx. So once I evaluate that, I will get the integral from x equals 0 to x equals 4. This is going to give me -4x plus 16. The second term will give me 0. So now I'm going to integrate -4x plus 16 with respect to x. So in order to take care of that integral, the integral of -4x plus 16 is -4 halves x squared plus 16x, and I'm going to evaluate that from x equals 0 to x equals 4. And so substituting in 4 will give me 16 squared, or sorry, 4 squared is 16. 16 times -2 is -32. 16 times 4 is 64, so plus 64, that's evaluated at 0. And then now when I evaluate it at 0, I'll just get 0 plus 0. And so my integral comes out to positive 32. And this again is going to be in cubic units, because when we look at what we did when we set this up, this had a unit of units, so it could have been height, some sort of height units like meters or inches or whatever, and dy is going to be a change in units times dx. So these are all things that are being multiplied together. And so I will get units cubed. Now that's not the only way we could have done it. That this was where dx was my outer integral. And that corresponded, again, the outer integral is what strip you're going to sum along first. So I wanted to sum along each dx strip, and a dx strip is the width of this column right here, and then the inner integral, because that's with respect to y, I'm going to sum, if you think back to our double summations, we're going to sum along all the different values of y before we move to the next x. But the other way we could have done this is by breaking this up into dy strips first. So breaking this up into individual rows like this. So visually, this is what we should think of when we're integrating on the outside dy. And notice that I'm breaking this up. I'm starting at y equals 0, and I'm breaking this up into horizontal strips until I reach x equals 4. So in this case, I'm sorry, y equals 4. So this is going to be from y equals 0 to y equals 4 is going to be my outer integral, and my function is, of course, 4, and then my outer variable of integration is dy. Now I have to think about, along each of these horizontal slices, where am I going to start and where am I going to stop? Well, to begin breaking this strip up into small rectangles, I'm going to start at x equals 0, and I'm going to keep on going, and I'm going to keep on going, and I'm going to keep on going until I hit the function. And then I'll move on to the next row, and I'll break that up beginning at x equals 0 until I hit, well, it's going to be a different value now of x. It's going to be until I hit the line again. And in the next column, again, I'm going to do the same thing, break that up into individual squares, compute their volumes, add up all those volumes to the running total, and I'm going to do it until I hit the line. Now, the line that we're referring to here is the line y equals negative x plus 4. But this tells me the value of y to go up to. I want to know the value of x to stop at. So if I solve this equation for x, and I get y minus 4 equals negative x, dividing by negative 1 on both sides will give me negative y plus 4. So we're arguing here that if we start at x equals 0 and go up to x equals negative y plus 4, that should give us the same answer, this 32 cubic units that we achieved up by slicing into dx strips first and then summing along all the dy's, we should get the same answer. So we can now evaluate this. We can again think about the inner integral first. So we want to integrate 4 dx, which is 4x, and that's going to be evaluated from x equals 0 to x equals negative y plus 4. And then, of course, we're going to need to have our outer integral there as well, so that once we're done with the inner integral, we can focus on that. So what I'm going to do here is I'm, again, going to evaluate 4x at the upper bound, which is 4 times negative y plus 4. Subtract away 4x evaluated at 0. And then once I get that answer, I'm going to integrate with respect to y from y equals 0 to y equals 4. Now, hopefully one of the things you're noticing is that our outer integral only has numerical values. If our outer integral had x in it, then once we integrated with respect to y, we would plug an x back in, and we'd end up with a function instead of a numerical value. And that wouldn't make much sense. So we always want to make sure that our and as long as you follow this logic, then you should never run into problems. But if you end up with a function instead of a value, then you know that something went wrong. Now this is going to be the integral of negative 4y plus 16. And already we're kind of seeing that we're getting a similar structure to our last answer, except now in terms of y. So the integral of negative 4y plus 16 will be negative 2y squared plus 16y, and I need to take that and evaluate it on our boundaries y equals 0 and y equals 4. So when I plug in 4, I'll have negative 2 times 4 squared plus 16 times 4, which that's our negative 32 plus 32. Subtract away negative 2 times 0 squared plus 16 times 0. That's going to give me 0, and I'm going to end up with an answer of 32 units cubed, which is exactly the same answer we ended up with doing it the other way around. So that's with working with a triangular region. And one other thing, doing this integration by hand is not a whole lot of fun, so we're going to go ahead and use a Wolfram Alpha applet that I'll jump over to next and show you how this applet will allow you to integrate the same functions, and we'll go ahead and start with this one here. So this is a double integral calculator, and you can see that it asks for a few things. It asks for f of xy. That's our integrand. That was the function f of xy equals 4. And then in here you see dA equals dy dx. So we just need to tell Wolfram Alpha what the order of integration is. Our first integral was in fact dy dx. It was dy as the inner, dx as the outer. So we're good there. We just need to set y to go from 0 to negative x plus 4. And we need x to go from 0 to 4. And now when we press submit, we should end up getting the answer, which is 32. And that is the volume that we came up with, obviously a much faster route. Now if I wanted to change this to dx dy, I would also have to change my boundaries, because now x is not going from 0 to 4, it's going from 0 to negative y plus 4, and y goes from 0 to 4. So we'll enter 4 in there and press submit, and if we've done everything correctly, we should get exactly the same answer we got before, which is 32. And you can see just by checking the integral that everything worked out and that everything looks the way we wanted it to. For this next example, suppose we want to find the volume under the surface, under the paraboloid, f of xy equals x squared plus y squared, but suppose that we want our region to be the unit circle. So the first thing I'm always going to do is I'm going to sketch the region over which we are hoping to integrate, and because my region is the unit circle, I am going to look at having a unit circle in here that's going to be 1 unit long in every direction, and I'm going to try my best to sketch a circle here. Actually, I can cheat a little bit, and we'll just say that's our unit circle right there. And so now I have to think about my boundaries. If that is a unit circle, that means this is negative 1, this is positive 1, this is positive 1, and this is negative 1. So again, what I'm going to think about doing here is I am going to decide in which direction I want to cut strips first. So I'm just going to go ahead and choose to slice this thing beginning at y equals negative 1 into horizontal strips like this. So notice that what we're doing here is we're breaking this thing up into dy's. Each one of these strips has a width of dy. So this is dy, etc. So notice where we started and where we stopped. We started at negative 1, we stopped at positive 1. So our integral would be y equals negative 1 to y equals positive 1. But now, and this is our function, x squared plus y squared, our outer integral is dy. Now we're going to focus on the inner integral, which is dx. And that means I have to sum the volumes, remember, because we have a z-axis coming right out at us, and we've got a paraboloid floating over this surface. Now, for each one of these strips, we have to subdivide them into regions beginning with to figure out what our left endpoint is and what our right endpoint is. So as I begin dividing, say, this thing here, it's a little bit harder to see, but I'm going to start at the left edge of the circle, and I'm going to break this thing up until I hit the right edge of the circle. For the next strip, I'm going to do the same thing. I'm going to start here, and I'm going to start dividing this thing up into individual dx strips, going from left to right until, again, I hit the edge of my circle over here. So the thing that we need to note is that the equation of the circle is x squared plus y squared equals 1. So for me to figure out what's the starting and ending x value that I need to go from and to, I have to isolate x in this equation just like we did in the previous equation. So I'll get x squared equals 1 minus y squared. Take the square root of both sides, and don't forget we need the plus or minus the square root of 1 minus y squared. And so this left edge right over here is going to be negative square root of 1 minus y squared, and the right edge of the circle is going to be positive square root of 1 minus y squared. So that's going to tell me that this integral right here needs to go from x equals negative square root of 1 minus y squared to x equals positive square root of 1 minus y squared. Now the alternative way we could look at this is we could divvy this thing up into dy strips first and then sum along the dx strips. But let's go ahead and represent this and calculate this in Wolfram Alpha. So I've gone ahead and put that in for us, x squared plus y squared. We have dx dy in that order. X goes from negative, you have to do square root sqrt parentheses 1 minus y squared up to positive square root 1 minus y squared. Y goes from negative 1 to 1. And if I compute that and everything worked out okay, I get about 1.57 as my answer. So now here we are back. We can say that this comes out to about 1.57. Again, we can compute this all by hand, but this is going to be a little tedious and it's hard enough to set these up. Now this is going to be 1.57 cubic units. The other way I could do this problem is by, again, dividing this thing up into dy strips. So let's go ahead and do that next. So here we have another representation of the function, and we're going to break this thing up into dy strips first. And we're going to start over here at negative 1, and we're going to begin slicing this thing downwards like so. And you guessed it, after we have this set up, we are going to need to sum up the volumes across each one of these strips. So our our x is going to go from x equals negative 4 to x equals positive 4. And our outer integral is dx. Our function is x squared plus y squared, so we want to know the volume under this paraboloid. And now we need to figure out how far in the y direction we need to go. Now I'm going to focus just on this strip right here. So I'm going to need to begin at the bottom half of the circle, and I'm going to continue needing to divide this up until I hit the top half of the circle. And same thing here. I'll go from the bottom portion of the circle all the way until I hit the top portion of the circle. And again, because we know that x squared plus y squared equals 1 is the formula for this circle, now I need to solve for the y value. So I'll do the same thing, and I'll get y equals plus or minus the square root of 1 minus x squared. And so our inner integral, the lower portion of the circle, is negative square root of 1 minus x squared. This is y equals, up to y equals the positive square root of 1 minus x squared. And we can compute this in our Wolfram Alpha app. We just need to change dx dy to dy dx, and I'm just going to go ahead and cheat here and copy that. So this goes from negative 1 to 1, and this is going to go from negative square root of 1 minus x squared to the square root of 1 minus x squared. If we've done everything correctly, we should get the same answer as we did before. And we get, lo and behold, the same answer, 1.57. So both of these approaches will work. It just sort of depends on what's going to be easier in the context of the problem. And we'll see situations where it's easier to integrate one way versus another. So in our next example, here we have a building. It's 8 meters wide, so it's 8 meters this way, and 16 meters long. It has a flat roof that is 12 meters high at one corner, so it's 12 meters high. We'll just put that point on the z-axis, and 10 meters high at each of the adjacent corners. So 10 meters high here and here. So we need to find, first of all, we want to know what is the volume of the building. And so we do have a nice rectangular region here, but we've got to figure out a function for this plane here. This is going to be a plane. F of xy is a plane. And we know that a plane has the format z equals mx plus ny plus some vertical z-intercept. And so I could figure out the change in z per change in x by noting that if this is my y-axis over here and here's my x-axis, that if I change x by 8 units, z will drop from 12 to 10, so that means z will drop by 2 units if I increase x by 8, so that's negative 2/8 x, plus, now in the y direction, when I increase y by 16, z drops by 2 again, so this is going to be negative 2 units of x per 16 units of y, plus b. And to get the value of b, I can note that this z-intercept point here is 0, 0, 12. And so that immediately tells me that my z-intercept is, so this is negative 1/4 x minus 1/8 y plus 12. And now I know what my equation of my surface is. So because this is a rectangular region, it does not really matter which integrals I pick, because if I chose x equals 0 to x equals 8 on the inner integral, then I would pick y equals 0 to y equals 16, and of our function, which is negative 1/4 x plus minus 1/8 y plus 12, and since my inner integral is with respect to x and dy, that should give me the same answer as inverting these two integrals. I do not need to worry about changing the boundaries because it is a rectangular region. So y equals 0 to y equals 16 of this function, negative 1/4 x minus 1/8 y plus 12, and this will be dy dx. So in Wolfram Alpha, I can go ahead and enter my function here. So we'll do negative 1/4 x minus 1/8 y plus 12. And it doesn't matter whether we choose dy dx or dx dy, but x goes from 0 to 8, and y goes from 0 to 16. So when I click submit, this volume that I get here, which is 1,280 cubic units, should be the same thing if I just change these two, because again, they don't have variable boundaries, they have constant boundaries. So if I change those, I should still get 1,280. So my final answer here is 1,280. And now because I know what the units are, we have meters by meters by meters. We're measuring everything in meters. So that means that here I have this quantity, which is measured in meters, multiplied by dy, which is measured in meters, multiplied by dx, which is measured in meters, and therefore my entire expression will be in meters cubed. So rectangular boundaries really don't matter in terms of which order you do them in, but of course variable ones do. So let's make this problem a little bit more interesting from our x squared plus y squared problem. Let's say that our region is a region that's bounded by the function y equals x squared and y equals 1/2 x. So what's that going to look like? Well, first of all, let's go ahead and graph it for 0 less than or equal to x less than or equal to 4. So first of all, y equals x squared is a parabola. Looks much like this. And then y equals 1/2 x is a linear function that will look like this. And what I want is, I just want to focus on the region that's bounded between these. So let's say this is x equals 4 right about there. And what I want is just the volume underneath this paraboloid within this region right here. So I can break this up into, again, do dy dx or dx dy. Now I've just chosen to actually modify this function to y equals x squared plus 1, just to make it a little cleaner. And so here, this blue curve, y equals x squared plus 1, and this green line, y equals 1/2 x, I want to find the volume between, under the paraboloid. So again, we have the z-axis coming out at us, and we just want to know the volume under the paraboloid under this awkward region. So once again, we can decide how we want to split this up, whether we want to use dx slices first or dy slices. I'm going to choose to break this thing up vertically first. So let's say that we broke this thing up from x equals 0 into vertical slices all the way up to x equals 4. Okay, and so that's going to give us the outer integral, and then we're going to stop here, of course, at this purple line. This purple line here. So we're going to have that integral go from x equals 0 to x equals 4. And now we're going to focus on the inner integral. This is of the function x squared plus y squared. We're doing dx on the outside, so dy on the inside. Now, where do we need to start slicing for each of these horizontal vertical strips? Well, we're going to start at the green line, and we're going to keep slicing until we reach the blue curve. Same thing here. Start at the green line, start slicing until you reach the blue curve. Start slicing here at the green line, continue slicing into dx by dy, these little area strips, and we'll stop at the curve. So the line is the line 1/2 x. The parabola is the function x squared plus 1. So that is one way to split this thing up. The other way we could start by doing is breaking this thing up into horizontal slices. And horizontal slices would mean I'd basically break it up, let's say right about there and here and so on, all the way across. Each one of these will represent one dy strip. And now we're going to break each of these strips up. So here we're going to start at x equals 0 or y equals 0, and we're going to continue breaking it up until we reach the highest value of 4. I'm not going to draw all of the strips, but we're going to continue breaking this thing up into strips until we reach the topmost point. So we're going to stop here when we reach this value of y, which is y equals 17. And the reason we know that's 17 is because that's where x squared plus 1 is when x is 4. So our integral here would go from y equals 0 to y equals 17, but our inner integral is going to have to go from the beginning value of x to the ending value of x. Now the challenge with this one, and the reason why it's important to know how to do dy dx and dx dy, is where we start kind of depends on where we are. There's this period right here where we start slicing over at y equals 0, right, for this first horizontal strip here, and then we stop until when we hit the line. But on these higher strips, we actually start at the curve and start slicing until we hit the line. So that's going to be a very difficult thing to break up. The question is, at what point, at what value of y do we begin starting at the curve? And that's going to be at y equals 1. So we would actually have to break this thing up into two separate integrals, not y equals 0 to y equals 17, but instead from y equals 0 to y equals 1. And that means x is going to go from, it's going to start here at x equals 0, and it's going to go until it hits the line. So since the line is y equals 1/2 x, that means that x is equal to 2y. So we're going to start at x equals 0 and go up to x equals 2y for our function x squared plus y squared dx dy. But we're going to have to add to that the total volume that we get by starting at y equals 1 and going up to y equals 17. But now we're not going to start x at 0, because now at x equals 1 we're starting at the curve and ending at the line. So here we'll have x equals, well, let's see, the parabola is y equals x squared plus 1. So that means the value of x that we'll start at will be x equals the square root of 1 minus y squared. And it would only be the positive one. The negative x's occur off over here on the left-hand side of the y-axis. So we want to go from x equals square root of 1 minus y squared until we hit x equals the line 2y. And you can see here we need to do two separate integrals in order to compute the total volume. And that was just our choice of whether we wanted to slice into vertical strips or horizontal strips first. In either case, you should be able to verify that these two separate integrals, that computing this one in Wolfram Alpha, computing these two in Wolfram Alpha, and then adding them together should result in exactly the same answer. One of the other important things is to be able to visualize the region of integration. So here we have a volume integral set up. We're not really concerned about the function itself. We just want to sketch the region of integration. So we notice that, first of all, the outer integral is with respect to x, which means we're going to be breaking this up into dx slices first. So that tells us that we're going to start at x equals 0 and end at x equals 6. But this integral tells us that we're going to start at x over 3. So y equals x over 3, or y equals 1/3 x. That'll be the line with a slope of 1/3 starting at the origin, and it'll look something like this. So this is the line y equals 1/3 x. And so basically this tells us that we're going to go from x over 3 to the line y equals 2. So when x is 6, right here, for this function, this actually is a y value of 2. Nice how that worked out. And so now we have a horizontal line coming across here at y equals 2. So this is the line y equals 2, and we want to, we're breaking this up into dx slices. So the way this integral is set up is, first of all, this gets broken up into these dx strips, and then within each of those dx strips, we're going from the line and breaking it up into individual rectangles until we hit the line y equals 2. So this whole region represents our area of integration. Lastly, we'll take a look at one application of when it's really not the case that we're computing volumes, but we're setting up our integrals as if we were. And the particular application is looking at the density of a material. So the density of a material can, in some applications, be thought of as the mass, which can be measured in grams, kilograms, etc., per unit of area. So if you imagine like a piece of metal or something, its density does not have to be the same all the way across. So you may find that the material is really just, by density we mean it doesn't have a lot of mass. It could be really light on this end, but then it could be really dense over here, meaning that if you were to just slice off this one corner, it would feel a lot heavier than, say, this corner over here. So that's measured in units of mass divided by unit of area. And whenever you multiply density by unit of area, so if you multiply the density of this sheet of steel by its area, you get, well, look at the units. Units of area cancel out and you're left with mass. So mass is equal to density times area. So to take a look at the application of this, suppose we have a triangular sheet of metal. The density varies as a function of the point xy along the plate. Suppose the density could be modeled by f of xy equals x squared plus y squared grams per square inch. So because this is the density, one thing that we should take away from this is that here at this point there is no density, and as we move farther into the xy direction, this is going to be a highly dense point up here because the square of 1 plus the square of 2 is going to give us a density of 3. I think in this case we're looking at grams per square inch. So that one corner right there has 3 grams per square inch of density. And that density varies throughout the entire sheet because the density depends on where along that sheet you are. So if we think about this formula up here, the fact that if you multiply density times area that you get mass, well, let's think about every one of these little tiny rectangles in here. If I look at that little rectangle right there, that's going to have some density over it. And if I multiply the density by the area of that little rectangle, that will give me the total mass of just that one point. So what this boils down to is we want some sort of integral over the entire region of our density function, f of xy, across the area. And if we think about this as density, grams per square inch, I think we were in square inches, and we multiply that by area, which is in inches squared, we're going to get total grams. So basically what we need to do is dA, recall that that is either dx dy or dy dx, depending on how we set up our integral. Now we need to know the equation of this line right here, and in order to know what the boundaries are going to be for the y value. And I like to personally have my inner integral be with respect to y if I know that this function is y equals something, because then I don't have to rearrange it and solve for x. So I see that it has a y-intercept of 0 and a slope of, okay, this is going to be over 1 up 2, so that's going to have a rise to run ratio of y equals 2x plus 0. That's the equation of that guy. Now if I break this up into dx strips first, that's going to make my job as easy as possible, because then I'm not going to have to solve for x in this equation. Not that it requires that much effort, but needless to say, it would be more effort than we would have to expel otherwise. So let's think about breaking this up into dx strips like so. And I'm not going to draw all of them, but so now we know that we're going to start over here at x equals 0, and we're going to end at x equals this point right here that falls along this vertical line. And that means that's going to have x going from 0 to 1 of our function. So our function is the function x squared plus y squared. And that's with respect to x. So y, for each of those vertical strips, we're going to start at y equals 0, and we're going to continue slicing until we hit the line. And in the next vertical strip, we're going to do the same thing, break that guy up until we hit the line. And so that means our inner integral is going to go from y equals 0 to y equals the line, which is 2x, and that sets up our integral. It's ready for computation. I'll let you verify this, but another way that you could do this is to have x go from 0, from x equals the line. So if I started over here at the line and worked my way to x equals 1, this would be x equals 1/2 y to x equals 1. And in this case, y would go from 0 all the way up to this point here, which is y equals 2, of the function x squared plus y squared. But our variables of integration would be dx dy. And that would produce us with the same answer. And you could check this in Wolfram Alpha.